Okay, we're going to look at practice D, which is electric field strength. So we're going to do D1 together. So first we're going to write our given. And just like with the homework that we did the last class, drawing a picture is essential. So it says a charge Q1. So Q1 is equal to 5 microcoulombs. Now before I go on, what I should do is I should remember micro is a prefix that means 10 to the negative 6. So I'm just going to rewrite this now because I don't want to forget to do it later on. And don't do anything fancy. Just say micro is 10 to the negative 6. And a second charge, so they're now telling me the orientation of where the charges are. So I'm going to draw my picture, and I'm just going to kind of draw my axis like this. This is the x-axis. This is the y-axis. So Q1 is at the origin. So what I'm going to do is at the origin, here's Q1, and it's positive. And I'm just going to label that as Q1. It says the second charge, Q2, so I'm going to write in my given, Q2 is negative 3 microcoulombs, which is negative 3 times 10 to the negative 6 coulombs, is on the x-axis, 0.8 meters from the origin. So I'm going to draw Q2 here. This is negative. But on my picture, I'm going to show how far apart these are. Okay. So the distance between these two charges is equal to 0.8 meters. And when I write my given and I do my picture and I have all my information, then when I'm doing the math, it's easy because then I can go back and look at everything. All right. So now it says from the origin, find the electric field. So now I want to find E on a point on the y-axis 0.5 meters from the origin. So now I want to find that electric field at this point here. And they tell me that this distance here is equal to 0.5 meters. All right, so basically what's happening is at this point, this charge is exerting electric field on this point. And then this charge is exerting an electric field on this point. So I'm going to have two different electric fields that I'm going to calculate. But what I need to do is first calculate each one and then find the resultant. So this is a positive. So we just learned that from a positive, the electric field goes in what direction? It goes out of positive. So this electric field here, I'm going to call this E1. So because this is positive, and electric fields go out of positive at this point P, the electric field on point P from this charge is going to go up because it's going out of the positive. All right. Now over here I have a negative. We just learned that the electric field goes into negative. So this is going to point this way like this, and this is E2. Now we're going to have to do some geometry here, because you see this is a triangle. So I have my given, I have my picture, and now I'm going to do the math. I want to find the net electric field. So what I'm going to do is I'm first going to find E1, then I'm going to find E2. Now these are vectors, so they have magnitude and direction. So after I find E1 and E2, then I find the resultant E. All right? So E1 is equal to K Q1 over R1 squared. So that's equal to 9 times 10 to the 9 Newton meter squared per Coulomb squared times Q1, which is 5 times 10 to the negative 6 coulombs all divided by, and now I'm going to look at the distance between Q1 and P, and it's 0.5 over 0.5 meters squared. So when I do all that on my calculator, E1 comes out to be 1.8 times 10 to the 5 newtons per coulomb. If I look at my units here, I would see that this coulomb cancels with that one. Here I have meter squared, so that cancels with that. So I end up with a newton per coulomb. So that's my unit for electric field. So this is E1. Now I'm going to do the same thing for E2. So E2 is equal to K Q2 over R2 squared. Okay? So it's going to be 9 times 10 to the 9 Newton meter squared per coulomb squared times -3 times 10 to the -6 coulombs divided by, now here's the part that's a little tricky. What is the distance from Q2 to P? It's not 0.8, it's not 0.5, it's actually the hypotenuse of this right triangle. So I could do it on the side, but you know what? I know Pythagorean theorem, so I'm just going to go like this and say 0.5 squared plus 0.8 squared, and then that whole thing is squared. All right? The square root of the two sides. If you want, you can do it on the side so you don't make a mistake. So when we put all this in our calculator, E2 comes out to be -2.9 times 10 to the 4 newtons per coulomb. Now, if this was all y and this would be all x, this would be easy to add. Okay? But because this is at an angle, we now have to figure out the horizontal and vertical component. So the next step is we're now going to put it in our table or chart because it makes it easier. The book doesn't do it like that, but I feel that when we do a table or chart, we're less likely to make a mistake. Okay? So we're going to have our E, and then we're going to have the x component, and we're going to have the y component. So we're going to have E1, we're going to have E2, and then we're going to have E total, and then we're going to have the x and the y. So this is EX and EY. So when I look at E1, E1 goes straight up. So when it goes straight up, that means it's all y. It has no x component. So this is 0, and this is plus 1.8 times 10 to the 5 Newton per coulomb. Now E2 is a different story. This is what E2 looks like. E2 goes like this. This is E2. So I have to find and remember, this is where I start. So this is, I go straight down. This is vector resolution. From the head of this vector, I do the tail of the other. So this is E2x, and this is E2y. And remember, I'm going to use my same sign convention that up and to the right is positive. Okay? Now, how do I find this angle here, theta? Well, you can use any trig identity you want. So if this is theta and I want to find theta, I can say tan theta is opposite over adjacent. So tan of theta is equal to 0.5 over 0.8. And when I do that on my calculator, theta comes out to be 32 degrees. So now when I want to calculate E2x and E2y, and there's probably an easier way. You can just do it by using the sides, but we'll just go ahead and do it this way. So E2x is E2 cosine of 32. So this comes out to be 2.5 times 10 to the 4. And E2y is E2 sine, because it's opposite, so it's 2.5 times 10 to the 4. Oh no, sorry. 1.54 times 10 to the 4. So now I'm going to put this in my chart. Now let's look at the picture. E2x, according to my sign convention, is this positive or negative? It's positive because it goes to the right. So I'm going to put this in E2x as, and this was like 2.5 something, so I think I rounded this. So this will be 2.6. Change this to 6 because it was like 5 something, 5, 6. 2.6 times 10 to the 4 Newton per Coulomb. And you see how E2y goes down? Well, according to my sign convention, up and to the right is positive. So I'm going to make this one negative 1.54 times 10 to the 4. So now when I add this up, EX is positive 2.6 times 10 to the 4. And EY, I'm going to have to find the difference, so then the difference would be plus 1.65 times 10 to the 5. So again, because this one was at an angle, there's a lot of steps. It's not anything difficult. Remember, I have a vector. I'm using vector resolution. I need to find the horizontal and vertical components. I'd use tangent because they gave me the sides to find the angle. Then, to find E2x, I said is E2 cosine of 32, because E2x is adjacent to the given angle, and then E2y is opposite, so I use sine. And then I put them in the chart. Once I get the chart, and you know in the book, if you look at the way they do it in the book, they don't do the table, and this way you don't make a mistake. So now, what did I just found? I just found E2x. This is positive, so this is my starting point. So now I'm going to have EX going to the right, because EX is equal to 2.6 times 10 to the 4. From the head of this vector, I do the tail of the other. So now here's EY, and this is positive, that's why I made it go up. So EY was 1.65 times 10. Oh, this is supposed to be to the 5th. This one. That was to the 4th. So this is to the 5th. And then from the head of this vector, I do the tail of the other. This is where I started. This is where I end. So this is my result in ET. Now, to find the magnitude of this, I use Pythagorean theorem. To find the direction, I use probably tangent. Remember, we're still using our standard sign convention that up and to the right is positive. So E total is equal to the square root of EX squared plus EY squared. So it's the square root of 2.6 times 10 to the 4 squared plus 1.65 times 10 to the 5 squared. So when I do all that, ET comes out to be 1.67 times 10 to the 5. But remember, my answer is not complete because all vectors, and this is a vector, have to have both magnitude and direction. So to get the direction, I always measure the direction from the tail of the resultant. And we did this in the beginning. Every time we did vectors, whether we did forces, whether we did momentum, anything that was vector, we've done this over and over again. So I'm going to say that tan of theta is opposite over adjacent. So it's the y over the x. This is the total. You can call it ET if you want. So it's 1.65 times 10 to the 5 divided by 2.6 times 10 to the 4. But then remember, when you get this value on your calculator, you're going to press second tan. So this angle comes out to be 81 degrees, but I have to say with the direction. So you see this 81 degrees is this way. So this is my plus x-axis. So I'm going to say 81 degrees above the positive x-axis. So that's my total answer. So if you look at your answer sheet, in parentheses, the final answer, it says 1.66 times 10 to the 5 newtons per coulomb, and then it says 81.1 degrees above the positive x-axis. Okay? So as far as the steps are concerned, again, we use the superposition principle to find the resultant vector, in this case being electric field, because we had a different field from each charge, Q1 and Q2. Okay? So again, it's a lot of steps. The math isn't difficult. You know, we use Pythagorean theorem. We use tangent. You know, basically that's what we did. So we didn't do anything that was difficult math. It was just a lot of steps again. And again, this is the hardest problem on tonight's homework. Okay, the other ones are a lot simpler. And that's it.